Hi everyone, I hope you're all doing well. Today we're going to continue chapter 9, which is all about acids, bases, and salts. And we're going to talk about a few properties of acids and bases, and we'll also talk a little bit about salts because salts are often produced from acid-base reactions. So previously I mentioned some properties of acids and bases. So I mentioned that acids taste sour, so that would be like a lime or a lemon. We talked about how bases are kind of slippery or soapy. So if we start with properties of acids, let's go into a little more detail. So acids, again, can taste sour, and they also produce hydronium ions when dissolved in water. So as an example, if hydrochloric acid reacts with water, hydrochloric acid will act, of course, as an acid, it's in the name, and then water will act as a base. So remember, acids will donate hydrogen ions, and bases accept hydrogen ions. So hydrochloric acid is going to give up a hydrogen ion, so then we'll have Cl- left over. And water is going to accept that hydrogen ion, so we end up with a hydronium ion. And other acids will do similar things as well. So they might not produce chloride ions, but they will produce hydronium ions. All right, so in addition to that type of reaction, all acids undergo characteristic double replacement reactions. So remember from before, in double replacement reactions, we kind of have two items that are switching places. And this can occur between an acid and solid oxides, hydroxides, carbonates, and bicarbonates. So previously, we did a lab involving carbonates and bicarbonates. So we'll go over those reactions again. And then we'll also talk about solid oxides and hydroxides. All right, so let's go over those reactions, and we're going to use hydrochloric acid as our acid. All right, so in this first reaction, hydrochloric acid is reacting with magnesium oxide. So this is our metal oxide. And remember, magnesium is in group 2 on the periodic table, and it is an alkaline earth metal. All right, so because this is a double replacement reaction, hydrogen is going to switch with magnesium, and we end up with magnesium chloride and water. All right, now what if hydrochloric acid reacts with a metal hydroxide, like magnesium hydroxide? We get the exact same products. We get magnesium chloride and water. However, the ratios between the reactants and the products are slightly different. So in the first reaction, there was a ratio of 2 to 1 to 1 to 1. And then in the second reaction, there's a ratio of 2 to 1 to 1 to 2. So we're producing more water in that reaction. Now, as you've seen previously in one of your labs, there's also a reaction with metal carbonate that can occur. So hydrochloric acid reacts with magnesium carbonate, and again, this is a double replacement reaction, and this will produce magnesium chloride, carbon dioxide, and water. So we actually end up with a whole other product here, which is a gas. But the other two products are similar to our previous reactions. And then if hydrochloric acid reacts with a metal carbonate, magnesium bicarbonate, for example, we end up with, again, magnesium chloride, carbon dioxide, and water. So these are all very predictable reactions that occur. This can occur with other acids and other metal oxides, for instance. So maybe instead of hydrochloric acid, we use nitric acid, which is HNO3. And maybe instead of magnesium oxide, we use calcium oxide. So hydrogen and calcium will switch places, so we'll end up with calcium nitrate and water. Now, of course, we have to balance this, so we need to put a 2 in front of nitric acid. So again, we end up with, some product and water. Now, that product is called a salt, and we're going to discuss salts later. Okay, so again, notice that each of those reactions we just went through can be rewritten in their net ionic forms. So what that means is we're going to remove all of the chloride ions, which are spectator ions. So that means they're not really forming a product, they're just kind of hanging out. So this shows that all acids can go through this same exact set of reactions. So we just showed that nitric acid goes through a similar process. We could use any other acid, hydrobromic acid, hydriodic acid, etc. And they'll all form these very similar products. So in this first reaction, instead of showing hydrochloric acid, we're showing hydrogen ions. And then in the products, we still end up with water, but then we have just our metal ion. And that's true for all of these reactions. So that's just the only difference here. And again, that metal ion will be attached to whatever well, not really attached to, but we'll pair it up with whatever spectator ion the hydrogen ion is attached to. And it will be aqueous. So again, remember, they're not really attached, they're just floating around solution. All right, so let's look at some examples of how acids can react with different materials that we're familiar with. So for instance, limestone, marble, and eggshells all contain calcium carbonate. So if we place these 3 different objects in acid, you'll notice that we can see reactions happening. There's gases forming in those solutions, but they're also kind of cloudy. So what's happening is hydrogen ions are reacting with calcium carbonate to produce calcium ions in solution, so those are aqueous, and then carbon dioxide, which is a gas, and then we're also producing water, which is a liquid. So here, let me add some symbols here for the states, and we'll also balance. Now, this reaction does occur in nature. If you've ever heard of acid rain is produced as an effect of pollution. So rain becomes a little bit acidic due to pollution and other sources. And if the rain that comes down is acidic, it can have an effect on statues over time. It can have an effect on like limestone over time. So those will eventually wear down, and you can actually find some pictures online of really old statues that have just worn away over time due to acid rain or other effects in the environment. Now, what they break down into, again, is this calcium ion, some gases, and water. Now, I also think it's really cool that eggshells contain calcium carbonate. So eggshells are a protective layer, but they can be worn away by acid. Now, acids can also react with certain metals and dissolve them. And they end up forming hydrogen gas in, remember, a redox reaction. So there's a transfer of electrons that occurs, and down below is a table showing different types of metals. Now this is called the activity series of the metals. So this is showing, a relative or relatively how well certain metals react with acid. So remember, a really long time ago we talked about group 1 metals like potassium and sodium. And we said that they are very reactive. They violently react with water. And remember, water can act as an acid or a base, kind of depending on the situation. So potassium and sodium will react violently with water. Calcium, which is a group 2 metal, it does react with water to a certain extent, but it will react more so with an acid, like a stronger acid, like hydrochloric acid. Let's see, and then below that are magnesium, aluminum, zinc, and chromium. Those metals will react slowly with hot water, but they'll react quite rapidly in acidic solutions, like hydrochloric acid. And then iron, nickel, tin, and lead, they react with strong acids, but not really with water acting as an acid. And then copper, mercury, silver, platinum, and gold are all really resistant to corrosion from acids. However, there are some acids that can dissolve those metals, but sometimes you have to mix 2 acids together in order to achieve that result. Okay, so just keep in mind that not all metals react equally. Some metals react really well with acids, some don't react very well with acids, and then some just don't react at all with acids. So here's a visual example of some metals reacting with acid. So down below it says metals vary in their ability to reduce hydrogen ions to hydrogen gas. This difference is apparent when copper, iron, zinc, and magnesium are put into hydrochloric acid solution of the same molarity. And then are these results consistent with table 9.5? All right, so in the first beaker, we have copper, and you can see it's kind of reacting. There's maybe a couple bubbles in that beaker. And then next to that is iron. There's a few bubbles forming above it, kind of a little stream of bubbles coming off of that iron. And then zinc is next to that, and you can see there's definitely more bubbles forming. And then finally, magnesium. Magnesium is reacting much more violently with the water. So let's look back at our table and make sure that this is consistent with what we would expect. Or I guess that's not water, excuse me, that's hydrochloric acid dissolved in water. All right, so copper is right here, and it says that it does not react with hydrogen ions, so it doesn't react with acids. And then we had iron, which does react in high concentrations of acid. And then we also had zinc, which reacts quite rapidly with higher concentrations of acid. And then magnesium. So if we look down this list, magnesium, zinc, iron, copper, magnesium should react the most violently with water. Hydrochloric acid, excuse me, I keep saying water for some reason. And then copper should react the least with the acid. So going back to this figure, we can see that that's true. Copper, I mean, there's a couple bubbles in there, but it's really not reacting compared to iron, zinc, and magnesium. And then magnesium is reacting the most violently with hydrochloric acid. Okay, so let's write down that reaction that's occurring. So magnesium is reacting with hydrochloric acid. And this is a single replacement reaction because we have an element and a compound. So magnesium and hydrogen are going to switch places. So we'll end up with magnesium chloride and hydrogen gas. And this probably looks pretty familiar to a reaction we've seen in our lab, or in a previous lab. But the other metals could have similar reactions with hydrochloric acid, except for copper, which really doesn't react with acid. All right, so now here we have the reaction of zinc with hydrochloric acid. Now remember that in these types of reactions, we can write the molecular equation, kind of similar to what we wrote on the last slide, where zinc reacts with hydrochloric acid to produce zinc chloride and hydrogen gas. But then we can also write what's called a total ionic equation. So zinc is a solid, so we just leave it as is. But then hydrochloric acid is aqueous, which means that it can be divided up into its ions here. And in fact, we saw previously that when hydrochloric acid is added to water, it dissociates into hydrogen ions and chloride ions. So we can write those as two separate entities in solution. Now, zinc chloride, the first product, is also aqueous, so that means it's also floating around solution in its separate ions. So we can write those as separate ions. And then hydrogen gas is a molecule, and it's going to bubble out of solution, so we're just going to leave that the way it is. Now, in this reaction, the chloride ions aren't really doing anything. So they're just spectator ions. So if we cancel out those spectator ions on each side of our reaction, we get our net ionic equation. So zinc reacts with hydrogen ions to produce zinc ions and hydrogen gas. Now remember, if you have a transfer of electrons, that's a redox reaction, right? A reduction oxidation reaction. So we could take this even a step further and assign oxidation numbers to each of these different ions and molecules. So zinc is a pure solid, so that would just have a value of 0. But then these hydrogen ions have a +1 charge, so their oxidation number would be +1. Then the zinc ion in the products has a charge of 2+, so its oxidation number is +2, or 2+, it doesn't matter which way you write it. And then the hydrogen gas is a molecule, so that's a pure elemental form of hydrogen, so we would give that a value of 0. So we can see that zinc is losing electrons during this process. So zinc, down below we can see, loses electrons to be oxidized. And then hydrogen is actually gaining an electron to be reduced. So we're going from +1 to 0. So it's becoming less positive, so it's becoming more negative, which means it's gaining electrons. And remember from before, we also went over what are called oxidizing agents and reducing agents. And remember, once you figure out what's being oxidized, it's the opposite agent, so it's the reducing agent. And once you figure out what's reduced, that's the oxidizing agent. So we're just kind of flipping the terms there. So if hydrochloric acid is the oxidizing agent, that means it's taking electrons from something else. And zinc is the reducing agent, which means it's giving electrons to something else. So it's reducing something. Whereas hydrogen is going to oxidize something. Okay, so this reaction occurs because zinc is above the reactivity line that divides lead from copper in the activity series. So let's go back to our table from before. So there's this line here between copper and lead, and that is the line that divides the metals that don't react with acid from the metals that do react with acid. And zinc we saw earlier is up here. That was the metal we were interested in that example. So zinc does react with acid because it's above that line of division. All right, so what's really nice about some of these reactivities or relative reactivities is that scientists have already done this work for us. So we have these handy tables we can look up to predict what will happen if a metal is added to an acid. But also, in this particular example, we combined a lot of different ideas. So we talked about molecular equations, ionic equations. We also talked about oxidation and reduction. So in chemistry, you really do have to combine a lot of different ideas all together when you're doing experiments. Now, this is also true in careers in medicine. You have to constantly think on your feet. You have to think of multiple different theories at once or multiple different possible cures at once. You know, what could be going on, what's going on with this patient. You know, maybe it's X, Y, or Z, and we need to narrow down what's actually wrong with the patient. So that can definitely be tough and stressful. But if you can handle doing that in chemistry, you can definitely handle that in a health-related career. All right, so let's talk about properties of bases. So earlier, remember we said basic solutions feel soapy or slippery to the touch. And we also said that they contain the hydroxide ion or produce hydroxide ions in solution. So one example is sodium hydroxide. If this is dissolved in water, we end up with sodium ions and hydroxide ions. All right, so the most characteristic chemical property of bases is their ability to react with acids in what is called a neutralization reaction. So let's show an example reaction between hydrochloric acid and sodium hydroxide. All right, so if these two react, this is also a double replacement reaction. So hydrogen is going to switch places with sodium, and we end up with NaCl, which is aqueous, and water, which is a liquid. And both of those products are neutral, so they really don't make a solution acidic or basic. It's just neutral. So if you think of, for instance, dissolving table salt in water, that's neither acidic nor basic. It's just salty. Now, bases can also react with fats and oils and convert them into smaller soluble molecules. So those types of reactions can occur in our bodies. Bases can break down fats and oils and try to make them more easy to digest. And then most household cleaning products contain basic substances. So lye in drain cleaner contains sodium hydroxide, and ammonia is contained in liquid household cleaners, and that's NH3. So here are some examples of different household products you might have or have seen before. So for instance, vinegar is also known as acetic acid. So that is a weak acid. So it's not super strong, but it's pretty effective at actually cleaning up mildew or mold. I had to use that this past winter because we had our rainiest January ever. But yeah, acetic acid also is contained in the vinegar that you would use on your food, so maybe on your salad. And obviously when you're eating salad with like balsamic vinegar on it, it does taste a little, acidic, a little tangy. Let's see. And then on the right-hand side, we have some cleaning products, so Comet, Windex, etc. And those are all basic. They're weak bases, but they are basic. Now, next to each of those cleaning products, you'll notice these little strips of paper. Those are called pH paper. So we can use that paper to detect whether something is acidic or basic. And we'll talk more about pH paper in a later slide. All right, so again, in neutralization reactions, an acid reacts with a base to produce a salt and water. So the following are typical neutralization reactions involving the base sodium hydroxide, which is also known commercially as lye. So we already went over the reaction of sodium hydroxide with hydrochloric acid, and we saw that we produce sodium chloride and water. So what if we switch out the acid for something different? So let's switch out hydrochloric acid for nitric acid. So a very similar reaction occurs. It's a double replacement reaction. So sodium and hydrogen are going to switch places. But instead of sodium chloride, we have a different ion attached to the hydrogen. We have nitrate attached instead of chloride. So we're going to end up with the salt sodium nitrate, and then we'll also again end up with water. So again, in neutralization reactions, you're always going to produce water and then some form of what's called a salt. All right, so in the first reaction, we produce sodium chloride. And then in the second reaction, we produce sodium nitrate. Now, both of these salts are neutral. They don't make a solution acidic or basic. They just keep the solution neutral. So let's talk about what salts actually are. So at room temperature, salts are solid crystalline ionic compounds. So you can think of table salt, for example. So the salt you put on your food is made up of tiny little crystals, and those have ions in them. So they contain a cation, which is a positive ion, and that cation is coming from the base. And then the anion, the negative ion, is coming from the acid. So NaOH, for instance, reacting with HCl, produced NaCl and H2O. So this is our salt, sodium chloride, and the sodium came from the base, and then the chloride came from the acid. So sodium is our cation, it's positively charged, and it came from the base, and chloride is an anion, it's negatively charged, and it came from the acid. So the cation, or the positive ion in a salt, can be any positive ion except hydrogen. And it will usually be a simple metal ion or the ammonium ion. So the reason that a cation in a salt cannot be a hydrogen ion is, remember, hydrogen ions come from acids. And salts are supposed to be completely neutral, so they're not supposed to be acidic or basic. So some examples of different salts are, for instance, NaCl, so sodium chloride, magnesium chloride. We could also have sodium bromide. Let's see, what else? Potassium chloride, etc. All right, and then the anion of a salt can be any negative ion except hydroxide ions. So remember, salts are supposed to be neutral, and if they do contain hydroxide ions, that makes them basic. So the anion of the salt, again, can be any negative ion except hydroxide ions. So up above, I used bromide and chloride. We could have used other anions as well, as long as it's not hydroxide. Okay, so salts can be formed in a number of reactions, and we've actually already gone over all of these different reactions. So remember, when an acid reacts with a metal like zinc, we end up with a salt and hydrogen gas, and that's always true for that type of reaction. And then when an acid reacts with a metal oxide, we saw that we form a salt and water. And then if an acid reacts with a metal hydroxide, we get a salt and water. And then we saw that if an acid reacts with carbonate or bicarbonate, we end up with a salt, water, and carbon dioxide. So we can produce a particular salt using each of these different reactions. It just kind of depends on what you have available. Now, in addition to these salts, we could have something called a salt hydrate. So when salts are obtained from water solutions by evaporating the water away, specific numbers of water molecules are retained. In some cases, as part of the recovered solid salt. All right, so for instance, let's say you just have salty seawater or ocean water or something. And let's say you leave it out, let's say you have like a cup of it and you leave it out in the sun and the water all evaporates. What you'll have at the end is some salt left on the bottom of the glass. But sometimes salts can hold on to water molecules, so they're not like completely dry. They do have a little bit of water left over. So some examples of hydrates, for instance, calcium sulfate can hold on to one water molecule, and we would call this calcium sulfate monohydrate. And this is something that's used in plaster, it's used in casts or molds. So it's a pretty useful salt hydrate. There's also, let's see, this molecule here, this hydrate, called sodium tetraborate decahydrate, also known as borax. That's used in laundry. And then if you've ever had to use water softener, this more so occurs in the Midwest, but you can have what's called hard water, and it just has a lot of ions in it. So sodium phosphate dodecahydrate, so that dodeca means 12. That is also known as trisodium phosphate, and that's used as a water softener. And yeah, so there's a lot of different examples of hydrates, which are really just salts that contain a couple of water molecules, or 12 water molecules. It just really depends on the hydrate. All right. So that brings us into the strength of acids and bases. Now, the strength of an acid or base is determined by the extent to which dissolved acid or base dissociates to form ions. So for instance, hydrochloric acid is a really strong acid. And the reason that it's a really strong acid is it produces a bunch of hydrogen ions. Or the other way to think of it is that hydrochloric acid dissociates 100% in water. So we would write that, for instance, with a single arrow. However, weak acids dissociate less than 100%. So for instance, let's find an example here. Nitrous acid, HNO2. HNO2 only dissociates a little bit or ionizes a little bit in water. So we would draw double arrows to show its dissociation, because most of the time, nitrous acid just remains nitrous acid. It doesn't really turn into ions in solution. So it's a weak acid because it only produces a small amount of hydrogen ions. All right, so there's a table in your textbook, table 9.7, that shows some common strong and weak acids. So hydrochloric acid, hydrobromic acid, nitric acid, and sulfuric acid are all really strong acids. So they dissociate 100% in water. And you can ignore this Ka value for now. We'll talk about what that is later, so just ignore that. Now, below that are some weaker acids. So phosphoric acid, sulfurous acid. Oh, my pen isn't working. Acetic acid, which we talked about earlier, which is in vinegar. Boric acid, carbonic acid, which is present in soda. And then nitrous acid. Those are all weak acids. So we've got strong up above and weak down below. So again, strong acids produce a bunch of hydrogen ions. Weak acids only produce a small amount of hydrogen ions. Now remember, we just saw that weak acids need that double arrow to show that they don't produce 100% hydrogen ions. So what that means is that at some point that reaction reaches equilibrium, where we have some fully intact acid molecules on the left and then some dissociated acid molecules on the right. That means we can write an acid dissociation constant for that equilibrium. So down below we have a generic reaction between an acid, and this is just symbolized with an HB, it's not an actual acid. And then water will act as our base. So again, the acid is going to donate a hydrogen ion to water, and water will accept that hydrogen ion. So we end up with hydronium ions and then our conjugate base. Remember, that's what is produced from the acid after it gives up its hydrogen ion. All right, so we can write an equilibrium expression for this. So down below, we've got our equilibrium constant, K, and that's equal again to products over reactants. So we have the concentration of the hydronium ions multiplied by the concentration of the conjugate base, divided by the concentration of the acid times the concentration of water. Now, we also normally would raise each of these concentrations to the coefficient, but if we look at our equation up above, all of the coefficients are 1. So we can just leave all of those concentrations as they are. Now, the other thing to remember is that water is a pure liquid. So its concentration doesn't change very much during a reaction. So we need to rearrange this equation. And we're going to put water on the left-hand side with K. Now K multiplied by the concentration of water gives us something called our acid dissociation constant, Ka. Now if we rewrite our expression, the acid dissociation constant Ka is equal to the concentration of hydronium ions times the concentration of the conjugate base divided by the concentration of the original acid. Also, remember that H3O plus and H plus are the same thing. So we could also write a simplified version of the acid dissociation constant, where H plus is just replacing H3O plus. And those are equivalent, so you could write this either way. And we'll just make it clear that Ka is the acid dissociation constant. Okay. So if we go back to that table that we were looking at for strengths of acids and bases, remember there was that value of Ka up at the top? So that acid dissociation constant tells us how well an acid dissociates in solution. So strong acids dissociate again really well. So their Ka value will be really large. And then weak acids, they don't dissociate very well, so their Ka values will be pretty small. And you'll notice that they range from 10 to the negative 10th to 10 to the negative 2, so those are pretty small values. Now, if we look at our acid dissociation constant, if Ka is really, really large, that means we have a ton of products. So if Ka is large, that means a lot of products. Which makes sense, right? We just said that if Ka is large, we have a strong acid. So it should produce a lot of hydrogen ions. All right, so just a couple more things before we go today. I know this is a bit of a long lecture. Some acids can actually give up more than one hydrogen ion, and we call those either diprotic or triprotic acids. So remember, we can also refer to a hydrogen ion as a proton because once it loses its electron, all it has is a proton left over. So monoprotic acids give up only one proton per molecule when dissolved in water. So mono means one. Diprotic acids can give up a maximum of 2 protons per molecule. So again, di equals 2. And triprotic acids can give up a maximum of 3 protons per molecule. So tri means 3. So off on the right-hand side is a table of different types of acids. So again, monoprotic means that you only lose one hydrogen. So there's something called butyric acid, which can only lose this hydrogen. Carbonic acid is diprotic, so it can actually lose 2 hydrogens. And then if we go down to phosphoric acid is triprotic, so it can lose 3 hydrogens. So just something to keep in mind with some acids. Some acids have more than one hydrogen. All right, so some common bases before we go. We talked about how ammonia is found in cleaning products. And this is actually a weak base, but it does react with water to produce ammonium ions and hydroxide ions. Now, the most common strong bases are hydroxides of either group 1A metals or group 2A metals. So sodium hydroxide, potassium hydroxide, those are very common strong bases. And then magnesium hydroxide and calcium hydroxide are some other examples. And I'll post some flashcards with some common strong acids and strong bases so you can kind of keep track of which is which. But I think we'll end there today. Next time we're going to talk about what are called indicators. So indicators tell us how acidic or basic a solution is. So I will see you then.